So today is 424, and if you're having to watch this from home, we're going to start looking at electrical power and energy concepts. So I want to start with a little concept-based question that you can do with your elbow partner. Two 9-volt batteries. I could connect them together to give me 18 volts of potential. A standard car battery is only 12 volts. Which is more capable of starting your car? Why? Turn and talk really quick to that person you're sitting next to. Which one's going to start your car? The 18 volt, 9 volts, the 9 volts connected together to give me 18, or the big 12 volt battery is going to start turned off? Which is more likely to start? And I have these models over here. Which one's going to do it? The 12 volt low voltage battery or the two 9 volts that are connected together to give me 18 volts? Yeah, thank you. Go ahead. The 12 line. That's really quick. It is. Maybe it's an obvious answer, but can you sort of explain why? It is the 12 line. I appreciate you trying. I ask this question every year in every class, and no one really understands. Intuitively, they get a sense of it, but they just have a hard time putting it into words at this point. That's okay. It's all about power, right? It's what is the rate at which you can deliver energy. Now, when I turn the ignition of my car, this thing goes through a very, very massive chemical reaction, and that provides a tremendous amount of energy at a high rate. And that's what I need to be able to start that car. So this thing can develop a lot of what's called power. Now these things connected together give me 18 volts. But when I turn it on, this thing would give a trickle flow, right? It just doesn't have a lot of capacity to deliver energy at a high rate. So you're not going to be able to start the car with 18 volts. Just like you're not going to injure yourself by touching a Van de Graaff generator that might be 100,000 volts. You have to have a lot of current. And the problem with those 9 volts is it doesn't have the current. So recall power is the rate at which we do work. In this case, we could also say it's the rate at which we transfer energy. So again, power is a transfer mechanism. It's the rate at which we do it. So for not just work, we could also say the rate at which energy is transferred. I'm going to write that in abbreviated form. So the rate at which energy is transferred. Now, how do we calculate power? We take the amount of current that's flowing through a device multiplied by the voltage drop. So when I talk about how much power a device is going to be able to deliver, if you will, I take the amount of current that is flowing through the device multiplied by the difference in potential that device is connected to. And I'm going to do a little bit for you, just off to the side, so to help you understand the units for this. So remember, power should be in watts. Which is the same as a joule per second. So when I said that was a 350 watt blender, that means 350 joules every second. Well, if I were to take a look at current is in coulombs per second. So let's go ahead and do I. That would be in coulombs per second. It's the ampere. And then multiply that by V, which is in joules per coulomb. Can you see that when I multiply those two together, the coulombs and the coulombs reduce out? And what I get is joules per second. So this would be in joules per second. When I multiply those things together, I would get so many joules of energy per second of time. That's what we call the watt. Now, I like to use mechanical analogies to sort of help us make sense of this. If I think of voltage as a height, sort of like from a gravitational standpoint, then each of these waterfalls would have the same voltage, if you will, the same height. But the amount of power, this would be a high power kind of stream because it has a lot more current flow. So if I were to put a little turbine down to the bottom to be able to harness the energy that's flowing over that waterfall, this would develop more power. These have the same voltage, if you will, but they just have lower power, lower current flows. Okay, so again, a mechanical analogy to maybe help you. if I were to have the same current flow, and again, I tried to find a picture on Google Images that showed the same amount of water flowing over these falls. The one on the right would have the same current as this one, but it's going to have more power because it's coming from a higher height, right? So we have more energy per amount of water there. The one on the left would be more of a low power arrangement. Okay. And so again, if I look at it from a mechanical standpoint, it's the amount of energy I'm able to harness from that water flowing over would be the rate at which that energy is being transferred is what we call power. Now, we're going to do a couple of calculations with this. There are 3 different equations for power I want to show you. And so one of them we already have is P is equal to I times V. I want to take this equation, and I neglected to give you a lot of problems on V is equal to I times R. So what I'm going to do is I'm going to take this equation and rewrite it in 2 different ways. So I would be equal to V over R. And I'll also say R, no, I'm going to leave it like that. So I could write it as I is equal to V over R, V is equal to I times R, or R is equal to V over I. So I could really take that equation and rearrange it any way that I want. I'm going to use versions of that equation with the power equation to rewrite power. So let's go ahead and switch this over to blue so it's a little bit easier to see. My base equation is power is equal to I times V. That's one of our equations. What I'm going to do is I'm going to replace that I with V over R. So if I were to take power is equal to I times V and replace the I with the V over R, what I get is power is equal to V over R multiplied by V. So all I'm doing is I'm replacing the I in that equation with V over R. Now I can combine those V squared, those V to turn into V squared. And I get another equation for power. If I don't know the current flowing through a device, but I know the amount of voltage I'm delivering to that device and what the resistance of that device is, I can calculate the power from V squared over R. The last one I'm going to do is I'm going to take the P is equal to I times V, and I'm going to replace the V with equal to I times R, and I'll get this equation. So replacing, I'm going to keep the I there. And then I'm going to replace the V with I times R. And I get my third equation for power. Which is P is equal to I squared times R. Now, it's not a math heavy class, so I wouldn't expect you to go through and do these derivations. But the tricky part of this is knowing which version of the power equation to use based on the things that are given to you. There are 3 things in electricity: voltage, current, and resistance. If I know 2 of those, I can find the amount of power being delivered through any one of those equations. Sometimes I know the voltage and the current. I can calculate them by multiplying those things together. Sometimes I know the voltage and the resistance, that's V squared over R. Sometimes I know the current and the resistance. So if I know any 2, I can calculate the amount of power. I just have to choose the appropriate equation. I have 3 or 4 examples for us to be able to look at, and then you guys will have a couple of questions to try on your own with that sheet. Electric space heater. Often you'll find these things down in the basement of a home where you might not have the best flow of heat from your furnace, and so sometimes you need to put a portable space heater there to try to keep a particular room a little bit warm. So it's a very high power device, 1320 watts. It's plugged into a 120 volt outlet. I just like to know the resistance of that device. So all I'm doing for this is I might make a little list of the quantities that are given. So it is a 1320 watt space heater. I plug that into the outlet that's 120 volts. And I'm asking I'd like to know the resistance. So if I do nothing else but just write the things down that are given and the thing I'm looking for, that will help me identify the equation that I would use. And so based on these 3 things, I would use this version of the equation, that power is equal to V squared over R. I'm looking for the resistance, so I'm going to rearrange that equation to get R. And a lot of kids will struggle with this if algebra is not their strong suit. Sort of like a cross-multiplying idea. The R in the denominator on one side has to be brought over to the other side, so R would be b squared over the power. Where do people make mistakes on this? Is that they'd say R is P over B squared, but it's not. R is B squared over P. A lot of times people will switch those things around. We go ahead and plug these numbers in, 120 volts. I'm going to square that, divide that by 1,320 watts. And we would get the calculated resistance of this device. And that's about 10.9 ohms. So that device, very small resistance. That means when I turn that thing on, I just have a flood. I have a huge flood of electrical current flowing through that device because the resistance is so small. All right, a small electronic device rated for only 1/4 watt. It draws a current of 35 milliamps. And what is the device's internal resistance? I'm going to make a little list, just like I did on the other one. It doesn't say anything about power, but you should be able to look at that and say that's a power value because of the unit. So sometimes students are like, well, what is that quantity? Sometimes you just have to look at what the unit is. When I say it's rated for 0.25 W, that means that that's its power. Now, current drawing is 35 milliamps. I'm going to write that first as 35 MA. But if I want to write that in terms of amperes, I'd have to move that decimal over 3 places because milli means 1,000. So that would be 0.035 amperes. And then I'd like to know the internal resistance. So now I'm looking for R. If you make that list, it might be easier for you to identify the equation. That would be useful. Take a look at that list of 3 values for power, and which equation would you use to calculate R knowing P and I? And I'm sure you can see that that power can be calculated as I squared times R. Since I'm looking for R, I'm going to solve that for R, for that. So I'm going to use the equation P is equal to I squared multiplied by R. I solve that for R. That would be P divided by I squared. That power is 0.25. The current from there, I have to put that in amperes, not in milliamps. I square that, and then I would get that value. Okay? So 0.25, divide that by 0.035 squared, and I'm getting about 204 ohms. That would be the resistance of that electronic device. Here's a practical application of this. Oftentimes, you are limited to how many things you can plug into an outlet or a series of outlets because those things are protected through something called a circuit breaker. Some of you know what I'm talking about with this. Yeah, anyone? You've heard? Okay, so I plug things in. If I plug in too many things into this wall outlet, I might end up tripping that circuit breaker that protects this thing. That circuit breaker that protects this is to keep things from you being injured and also from like a house or a building being burnt down. So you're going to have some protection devices here. Let's say I have these 4K televisions and I'm a dealer and I'm trying to sell these things and I want to have these things plugged in on display. I can only plug in so many TVs on this service before I trip that breaker. It's a 15 amp service. That means anything more than 15 amps being drawn from that circuit is going to trip that breaker. Each TV is 350 watts. I plug them into a 120 volt outlet. Question is how many TVs can I plug in before I were to trip that breaker? Okay. So let's see. I have quite a few things going on here. First thing I might do on something like this is I might determine the amount of power available. So I'm just going to I'm going to see if I have a 15 amp breaker, then I might say, well, how much power do I have available? I did not smell that right. You guys ever have that issue where you're like, I know I made, how did I spell that right? What do I have to fix? I have to switch those things around? Yeah, sorry. Sometimes like, you write things and you're like, wait a minute, what am I doing? I did something wrong. You're saying it's got to be this. Yes? I'm sure you guys have had that happen before. Just happen. All right, power available. I'm going to say the current that's available multiplied by the voltage. So I'm going to go back to the idea that power is equal to I times V. I'm going to say, well, how much current do I have available? So I available, and of course I wrote that incorrectly as well. Maybe because I didn't want to try to spell available again. But I did it correctly this time. So if the amount of power available is how much current I have available multiplied by the voltage, I can do that. I have a 15 amp service. I'm multiplying that by 120 volts. And what that means is that the amount of power I have available is 1,800 watts. That's what I can actually have running on that service. By the way, this toaster, I think you said this was an 1,800 watt toaster, correct? This is it. This is all I can plug in. I plug this thing into that service. That's the only thing I can plug in. Anything more, and I'm going to trip that breaker. So if I'm using TVs, and those TVs are, oh my gosh, that was just by chance that the wattage of the TVs were the same as this. But how many of those TVs could I have plugged in? Some of you, I'm sure, are seeing that right now. I would just take that 1,800, divide that by 350. And I would get 5.1 TVs. Now, obviously, you can't plug in 0.1 of a TV, so you could plug in 5. But you plug in 6, and that would be enough to trip that breaker. So the number of TVs that you would have is 5 TVs. Anything more than that, you're going to trip the breaker. Okay. I'm going to ask you guys to try that number, that last one. Just see if you can get through it. It is an electric heater. It's operated by applying a potential difference of 50 volts across a wire of total resistance 8 ohms. I'm looking for 2 things. Find the current in the wire and the power rating of the heater. Now, we had to sort of rush through this yesterday, so I'm going to tell you you're going to need to use both equations. You're going to have to use the relationship between current, voltage, and resistance. And you're also going to have to use some value of power, right? So it's either going to be I times V, V squared over R, or I squared times R. So go ahead and give that a go. See if you can go through and manage the values that are there, and we'll see where we are. Okay, give it a go. So if you're watching this from home, you should try that one as well. I'm going to write up the solution without talking through it, so these guys can work without me talking to them, and you should also try this at home as well. I didn't talk through that as you were working, so you could try to work independently from that. I calculated the power with all three equations because all three should give me the same value. If I find the current first with I is V over R, I get 6.25 amps, and then I could use technically any one of those equations because I know all three values, V, I, and R, so I can calculate the power to be either I squared times R, I times V, or V squared over R. I get 313, about 312.5 watts. Okay? How'd you do? All right, we have one last topic, and sorry for rushing to do this. When we talk about energy for electricity, the joule is way too small of a value. So we typically use something called the kilowatt hour. Kilowatt hour is a new unit for you guys, and the kilowatt hour is what you would see on your electricity bill if you were to, when you start paying for your electricity, you'll see that it's measured in what's called the kilowatt hour. Now, I stole one of these meters from my neighbor. I'm joking, I did not actually take this from my neighbor's house, but this is an old school kilowatt hour meter. It's something that you would see where your electrical service comes in from the street. You would see something like that where it comes down, before it goes into the home, it's going to go through a meter of this type. Now, they've been replaced with something, this is mechanical, but they've been replaced with something that's more electronic now. They're also tied into the web, so if the power goes out, they know that your house is without power. They don't need to have people call in for that. These things could not give that kind of feedback, so they end up replacing a lot of these things. This is what's called a kilowatt hour meter. That measures energy use. Now, if I take a look at this equation, powers work over time, I could say that energy is then power times time. So I would take the amount of power that's being delivered, and I multiply that by how long it's being delivered, and what I get is the kilowatt hour usage. Okay, so again, energy is power times time. I'm going to have my power being measured in kilowatts. So that has to be in a kilowatt value, and that has to be in an hour value. So what I'm going to do is I'm going to multiply those two things together to get the amount of energy. A 1 kilowatt hour amount of energy would run a 1,000 watt device for an hour. So if it's a kilowatt and I run that for an hour, that would be 1 kilowatt hour of energy. Now, if I'm using energy at half the rate, so it's 500 watts, if I run it for twice as long, I would use the same amount of energy. It's like someone that makes $10 an hour could make the same as someone making $20 an hour if the $10 an hour person works twice as long, right? So you can get the same amount of energy use by using that thing longer. How long could I use a 100 watt device before it uses 1 kilowatt hour? It'd be 10 hours. And then finally, a 6,000 watt device, if I run that thing for 10 minutes, that would use a kilowatt hour of energy. Where would you likely find a 6,000 watt device in your home? This right here, if you have an electric oven, if you used an electric oven, that would probably be a really high power device. A lot of ovens are gas, but if you have an electric oven, you would know because you have the coils that sort of glow red or orangish or so on the surface. You turn it on, you look inside, you see some red glow from the electrical energy being converted into heat. Okay, it is technically equal to about 3,600,000 joules. Now, this is written in scientific notation. The kilowatt hour is a lot of joules. So when you measure electrical energy use and you get your bill, 1 kilowatt hour is equal to about 3,600,000 joules. The joule is just a really small unit of energy, so we use the kilowatt hour. Okay, I'm going to do a couple of problems with you just to show you how to compute your energy bill, and then that'll stop. And again, folks, I apologize. It's such a lecture-intensive day. Coffee pot brewed for 45 minutes a day, 30 days a month. I just want to calculate the amount of energy used. So I look over at this table. Coffee pot, it looks like that coffee pot is a 200 watt device, and I'm using that for 45 minutes a day, 30 days a month. I want to calculate the amount of energy used. So let's go ahead and try that together. I want that power to be listed in kilowatts, and that'd be 0.2 kilowatts. 45 minutes a day, well, that'd be 45/60ths of an hour. So I'm going to write that as that much of an hour. And then since I'm doing that every day, I'm going to multiply that by 30 to get the total amount of kilowatt hour energy use over the course of that month. So again, make sure your power's in kilowatts, your time is in hours, and then compute that just by adding those things together, or multiplying those things together. That would give me about 4.5 kilowatt hours. So at the end of the month, your energy bill for electricity would be about 4.5 kilowatt hours higher due to the use of that coffee pot. Raise your hand, waffles. Raise your hand, pancakes. If you had to choose, waffles, pancakes. Okay, looks like the waffles won. If you're watching this from home, the people in here voted for waffles. So in waffle iron, making 6 waffles, each taking 7 minutes. This is done weekly, so 4 times in a month. I want to calculate the amount of energy use, and so let's give that a go. Again, I look over at the table. It looks like the waffle iron is a 1200 watt device. So I'd say energy is power times time. That power is going to be 1.2 kilowatts. I'm making 6 waffles, 7 minutes each. So I'm going to say that that is 42 minutes. And that's 60 hours, or 60 minutes in an hour. So it'd be 42/60ths of an hour. And I'm doing that, it looks like it's done weekly, so I'm going to multiply that by 4 because I'm doing that 4 times a month. And so the amount of energy used for that, 1.2 multiplied by 42 divided by 60. And then multiply that by 4. That would be about 3.36 kilowatt hour of energy. So if I'm making waffles once a week, my energy bill at the end of the month would be that much higher due to that. I want you guys to try number 3 and 4. I'm just going to give you both of those. Give it a go. And that's probably a good stopping point. And actually, that has to be our stopping point because I have to give you guys some time to work on those problems. Take number 3, take number 4, see if you can go through and try both of those. Take a look at that table off to the right to be able to do it. Hopefully you're trying this at home as well. I'm going to go ahead and write the answers up without talking. And hopefully you had a chance to try those as well. I didn't try to talk through that as you were doing those. Should have gotten 2.5 kilowatt hours and 1.28 kilowatt hours. Zoom in really quick for you. This was what it looked like back in 2011. This is where the electrical energy was being delivered to your homes. Most of it's going into space heating and cooling. Then you have water heating, and then lighting and so forth. 2025, probably, I'm going to guess that the lighting has gone down because of all of the lighting has gone down. Largely because all of our light bulbs have been replaced with LEDs, which, as opposed to the incandescents, are much more efficient. Probably the electronics has probably gone up, is my guess. Right? We have more electronics in our homes today than we had before. We still have a lot going into space heating and cooling, especially during the summer months when we're using an air conditioner to try to cool our homes, and water heaters. Again, some of them are electrical, but that's what we're. Okay, guys, I'm going to stop. I apologize a lot of talking. We do have our quiz tomorrow, and we have to hit those dates because I have to sort of schedule those things in advance. So we're a little bit of a rush. I'm giving you a few problems to try in the time that you have, which is almost 10 minutes, which doesn't seem like much, but there's only 6 questions here. Give those a go, see what you're able to do, and we'll get these by tomorrow. Okay, so if you don't finish it, that would become quote-unquote homework or academy time work, but I need those done by tomorrow, okay? Questions for me? All right. How about I do this? I'm gonna have you give me a grade out of 10 as you guys are working. I'm just gonna call your name. You give me 5, 10, whatever. Just hold up numbers and fingers there, and I'll take you at your word for that one. So I want you guys to have that in case you need to study off the thing. Okay. All right. Yeah, better.